Hi folks, I'm Vanessa Socket. I'm a computer scientist at Lawrence Livermore National Laboratory. And today we are going to be talking about snapshotters or faster container pulling in Kubernetes, or as I like to think of it, this is going to be a code journey from schedule to snapshot. Let's get started. So at the end of August, we ran a very large performance study. It was across 3 different clouds. We use all 3 flavors of Kubernetes for both CPU and GPU across the applications that you can see. So even just on this small matrix, you can tell that there's a lot of container pulling going on. Guess what? Each of the sizes of cluster that we ran was a separate cluster, which meant a different set of pulls. So when we look at the individual clouds, brr, is it cold in here? This is going to be a lot of cold starts. A cold start is the delay that you get when you're starting an application. What does this actually look like? Well, for cloud A, it was about 8.5 and 4 hours total pulling. Cloud B, a little bit of a different pattern, still a lot of hours. Same with cloud C. Now, I'm not going to go into the nuances of the differences between the clouds. This is not what the talk is about. I want to make a point, however, that our containers were designed to be redundant. So what you're looking at here is a similarity matrix, specifically the Jacquard similarity. And this is comparing all containers pairwise. And what's really cool about this plot is that you can actually see the different cloud setups. So in the top left, we have AWS and Google for GPUs. Then we have them for CPUs. The reason they're so similar is because the only difference between these containers is that AWS has libfabric. We then see Rocky bases for compute engine. We were suggested to use Rocky there. We then see Azure GPU and Azure CPU. These are distinct because we needed a different install because of InfiniBand. And scattered in there, we'll point out, are a few SPAC Snowflake builds. So when we summed up the time, it was almost 60 hours. 60 hours pulling containers. So mind you, this is like spread across the nodes. So I wasn't actually sitting there for 60 hours. But time is money. We would want to minimize this value to the maximum extent that we can. So how much could this be improved? This was my question after we finished this study. And oh my goodness, I did not know. I didn't know after the study. This was me, the third squirrel. So I started to look into this. What are strategies for getting optimized container pulling in Kubernetes? So the first idea is like, well, use a solid state drive with better IO. When you're pulling and extracting, it might be a little bit faster. Reasonable idea. The next idea was to use something called image streaming. And, at the time, I had no idea what that was. Hint, this is eventually going to be snapshotters. And then another idea, well, you can use a different compression algorithm. So Z standard compression is about 3 times faster than gzip. We can also preload images. If we're using a common base image, we can preload them onto the nodes with some mechanism. And if you go back like 10 years, the advice is that you'd hear is just like, build small containers, multi-stage builds, apt-get update, apt-get clean, make them smaller. But the machine learning, we cannot do this anymore because the machine learning images are freaking huge and they're not going to get any smaller. Okay, belabored that point. So I decided to focus on these 2 approaches because the other 2 felt like they might have feet, but 1, people probably aren't going to want to figure out how to use custom compression algorithms, when they're building containers. 2, it's probably the case that you're not going to have all your containers have like a common base. So these are good ideas, don't get me wrong, but I decided not to test them. I decided to test these 2 here. So I came up with an experiment plan, a container pulling study, and the first question I had was about the number of layers. And of course, if you have a cake, more layers is better. Actually, I'm not sure about that if like the fork can't like make it through, but that's a different experiment. So I made a tool in Go. It is called the Container Crafter, and that is what it does. You can generate a Fox matrix of containers across a number of layers and sizes. And the reason that this tool is important is because it guarantees that each one of those layers is absolutely unique. So there can be no caching. And so I was going to build across a number of layers. I wanted to figure out if the number of layers was actually important. And then I wanted to test pulling onto solid state drives and image streaming. And here is what it looks like to use my tool. So you target the study.yaml file that has your parameters in it. And then you basically are building a bunch of different digests under a common URI. You push them all those tags through registry just like this. Okay, so the first thing I quickly learned is that the number of layers absolutely does not matter. So what you're looking at here is going across the number of layers on the x-axis 1 through 100, and then the pull time on the y. And so this is ranging from 43 MB, so pretty small, to 19 gigabytes. And what do we see? Well, what we see is that the number of layers like really doesn't seem to matter. At best, it seems random. The variable that seems to matter here is the image size, okay? And now, if you step back though and think about this, let's pretend for a second that I actually did find a number of layers that was like better. Let's say that 4 layers was the magic number. Now, do you really think I could go out to the container community and be like, thou shalt build images with 4 layers? No one would do that. People are going to do what they need to do, what they want to do, and it's going to have some number of layers. You can't tell someone to build an artificial number of layers. So for my study, I decided to use what from the data. So the data set that I had built was 77,000 Docker files from the scientific community. The magic number is 9. So I was going to do my study looking at 9 because that was sort of the mean or the median. I actually don't remember which metric I used, but that was a good representative value. So this is what my study.yaml looked like. You'll notice that I go across sizes up to the 100th percentile, again, from this big database that I built. And I'm going to build 2 sizes, 9 and 125. And so let's first look at the impact of a solid state drive. So this is using a persistent disk. You'll notice it takes about 150 seconds, 155 seconds maybe. For the largest size, that's consistent across cluster sizes, 4 to 256 nodes. When we use a solid state drive, you get about 35 seconds back. Not bad, but still not really anything to call home about. Not that exciting. Now, are you ready for the streaming? The fish and the layers. I hope you see that reference. Okay. I made this plot and I was shocked. I was like, well, I didn't believe it. I said, there's no way that my container is running in a second and that the outliers in this plot are like 3 or 4 seconds. There's just no possible way that the cake looks like this. So I was as skeptical as I think I've been in a really long time that what I was looking at was absolute nonsense. And of course, when this happens, this is when you step back and you want to really understand how something's working because you want to know what's going on, right? It makes sense. So I went to a bunch of these repositories. I started learning that it was containerd with these Snapshotter plugins. This is the quote that I saw in a lot of these repositories, that image download is taking a huge amount of startup time, but guess what? Only about 6.4%, a really small amount of that fetch data, is actually needed when you start your container. That's from Harder et al. Fest 2016. That's really interesting because this is something we can use to build a tool that maybe can do this process a little bit better. So what is going to be involved here? This is what I knew when we started. I knew we were going to be dealing with Kubernetes. There's going to be the control plane with a scheduler. It's going to be the kubelet with containerd and something else magic in there so that by the time that I get to eat my cake, somehow it has been delivered to me in a very optimal way. I don't know. So this is where we're entering the deep dive rabbit hole because we are going to go from how does a pod start from being scheduled on the control plane to running a container. Just a warning, some of the infrastructure diagrams I'm going to show here are very high level. That's meant to be just for this talk. Doesn't actually reflect the Kubernetes ecosystem, which I hope you know is very complicated. Okay, so we're going to start in the control plane that processes requests and schedules pods that has kubesched and the API server. That is going to go to the kubelet. The kubelet manages the pod and the nodes. There's also containerd running alongside the kubelet. And the API server is basically orchestrating communication between these 2 components and other components too. So here is the scheduling cycle. This is the entire scheduling context, which includes basically when you submit something, it gets sorted, goes through the scheduling cycle and the binding cycle. We're very briefly going to go through this. The way this is designed is by way of plugins and extension points. So if you make a custom scheduler plugin, for example, you'll implement some subset of these endpoints. Just as an example, when you start, and for example, if you want to implement a plugin that does sort, you will implement this less function. This is an example from the Kubernetes SIG co-scheduling custom scheduler plugin. It sorts based on priority, creation timestamp, and then the namespace. So first, your pod goes through scheduling cycle, basically the different filters, choosing the nodes, ranking the nodes and scoring, and then reservation and permit. It can be rejected at any point in the cycle. So if your pod makes it through the scheduling cycle, you get to the binding cycle, which is what it sounds like. This is where you're basically going to have a request to say, okay, this pod needs to be bound to this node. Here's the name of the node, and here's the pod. Off you go. That's going to be done via the API server. So here we are in that function. We basically run the scheduling cycle function. We get back a result. Then in this go routine below it, we basically are going to be running the binding cycle. The binding cycle actually isn't like directly doing something. It's running another plugin. Specifically, it's running the bind plugins. And in the bind plugins, we're actually using the Kubernetes API client. So those are those lines at the bottom to send over a message that says, okay, here's the target. It is a node of kind node. And here's the node name. Off to the API server you go, and the kubelet is going to somehow receive this. So we're in kubesched. We sent over our pod to the API server. Now let's jump over to the kubelet. How does the kubelet get it? Well, this was actually very hard to find, but when you're basically setting up the kubelet and you're configuring it, it creates this API server source. It is receiving an update channel from the main kubelet function. Basically, that's going to be passing something back. What is the something? We can trace this function, new source API server, from LW, which is a list watcher, passing the channel. In that function, we basically are receiving the messages. We're packaging them into pod updates, putting them back into that channel, and that's going to go back to the main kubelet. And then we're going to be acting on the kind of instruction that we get. So add, update, remove, reconcile, etc. I won't go into all of these, but let's just look at add. So add is going to call a handler to call handle pod additions. Handle pod additions is basically going to pass this pod into the pod workers. So it's basically going to be creating this worker on demand. In the workers, we're going to be calling this pod worker loop. A lot of these things have like loops. That's an interesting design pattern. Once it's in the pod worker loop, it kind of checks for different states. Is the pod terminating? Is it doing something else? If not, it gets the default that we're going to this pod syncer. We're going to be syncing the pod. What does that mean? Let's look at the function. Interesting. Here's the first time we see the kubelet, so that's KL. Calling the container runtime sync pod. Okay, we're getting closer. The container runtime, okay, finally, we're computing something called pod actions that's actually going to be changes for sandboxes and containers. That function, finally, we see interactions with the container runtime interface of CRI. So start container, and then below it, ensure image exists. And it's when you go in this function, ensure image exists, that you finally see a call to pull an image. So this is kind of what we were looking for. We wanted to see the message received, and then we wanted to see some requests to pull the image. So in the pull image function, this is going to basically make a call to the image service to pull the image. That is right there. We go into that function. Here is where we finally see calling the container runtime interface to CRI. So as a reminder, the CRI is the main protocol for the communication between the kubelet and the container runtime. When you see something like a protocol in Kubernetes or just generically in Go, folks, you are going to see protocol buffers, gRPC. So here on the left, we see the message for pull image that has a particular message pattern. So for the request and response, that's what we see on the right. That is exactly what we saw here in this service, that pattern right there. So now we are seeing the kubelet make a call into the upside down to the Demogorgon that like lives there. Like, what's going on between here? Well, okay, hold on. Let's quickly remind ourselves what the heck containerd is. So containerd is managing the complete container lifecycle of the host system. So this is the node from image transfer to storage and container execution and supervision, low-level storage and network attachments and beyond. So maybe it is a Demogorgon because but it's like a Demogorgon with like lots of arms because he's doing all these things at once like that. this is my understanding of containerd, and it's running via gRPC. So there is the upside down. Cue Stranger Things, great TV show. Okay, so containerd is running via systemd. So here we see the service file on the left. We see it running on the right on my little dinky kind cluster I was testing on. So now we're looking at containerd source code. So this is in the entry point, the command. The init process is eventually going to serve this gRPC endpoint. We see that it has, so this gRPC cry image service also has a pull image. But hold on. Let's step back because what was this talk about? This talk was about Snapshotter plugins. We haven't really talked about them yet, so let's do that. A Snapshotter plugin is going to manage the creation and manipulation of your container image layers. If you have a special kind of Snapshotter plugin, it is actually going to do lazy loading of container images too. So containerd is going to have these snapshot plugins. What does this actually mean? Well, it has a configuration file. So that's the file on the right. This is an etc containerd config.toml. What you see here is the default snapshotter. So the default snapshotter is overlayFS. And conceptually, what that means is that every time you have a layer, you prepare a snapshot. So you have a directory, you extract the layer, you handle like whiteout files, what have you. You check it against the digest. Okay, great, you have a snapshot for a layer. You do that for next layer. You add it onto the parent. You check the digest. You have to do that incrementally for every layer before you hand it off to actually run the container. And so that's why it might take a long time. So that's the default. By the way, the service is delivered, so the messages are being communicated over a socket, a Unix socket, not a Vanessa socket, Unix, Vanessa, different sockets. Okay, so this is when you're starting containerd, this is the init. So this is a function called load plugins. Lo and behold, we are loading snapshots. There's other interesting plugin types in here that I recommend you check out if you're interested. And here is the equivalent. So to go back to this pull image, we're calling the CRI image service pull image. That is preparing our snapshotter. It's preparing pull options that hand over the snapshotter. And then you're making a call to the CRI image service client pull. Are we getting closer? I hope we're getting closer. And so when you see this, you're like, what is c.client? C.client is an image client, and it's on the CRI image service. And if you look at the interface of the image client, this is what you'd expect to see. List images, get images, and pull. How does this work? Well, at the init or the start of containerd, you have a built-ins package. And this is also where you see the services. You see there's an images service and a runtime service. That is imported in the main function for containerd that you see on the right here, that built-ins. And if you're familiar with Go, you know that the underscore pattern is basically going to import the package. And if there's an init function, it's going to call it. And so conceptually, when containerd starts, these plugins are loaded. Lo and behold, here's the init function. The init function is creating this new images service. And then the new images service has the client. This is how it all comes together. It's just magically there. So when we go back to this client.pull, we now can look at the pull and we see that the pull is going to be unpacking. Okay, getting closer maybe. And finally, in unpack, this is where we see interactions with the Snapshotter interface. So when you look at what a Snapshotter, the functions it needs to implement, you see a generic set of them. So there's this set that you see here. I'm going to go over a couple of these. Not shown are update, mounts, view, and usage. I'm not going to go over them in detail because this talk's already really long, but go check them out at the repository. We're going to be talking about prepare and commit in detail. So to remind ourselves of the Snapshotter plugin, we're going to be managing the creation and manipulation of container image layers. This means, in like Vanessa layperson terms, like, hello, I'm the Snapshotter. When you call prepare, I'm going to make you a special little directory that I'm going to be dumping layers into until some point. Maybe I'll have an original set that I dump. I'm also going to have some metadata to help me along the way. And when I get to some point when I think it's good enough to represent a file system of some number of layers, I am going to commit and I'm going to provide it to you, this lovely layer cake, as a root file system for your containers. So we're at like slide 100, and we're just getting into the topic of this talk, but not really, because so the SOCI snapshotter came from the stargz snapshotter. Stargz means Seekable targz. So just for some background, a standard layer is a targz. It is like a hard-coded, stony, cold stone ice cream. That's an ice cream store. I always think of it as just like this stone that is frozen. It is not seekable. If you want to find something, you have to like read the whole thing. And yeah, you can't change it. So Seekable targz is going to change that. Also, if you thought of like stars, this is another way to think of stargz. It's just like making your eyes. This is actually what I originally thought. That was basically me when I wrote about stargz. But then I was like, oh, it's just Seekable. Anyway, let's continue. So what if I told you that groups of targz are valid targz? Matrix. Actually, it's true. gzip streams can be concat and still be valid gzip streams. And so if you look at this blue box on the right, that is what a traditional targz looks like. You have a gzip of some number of tar files and then a tar footer. With stargz, you actually have gzip in there, and then look at the second to last. That is going to be an index. We'll see what that looks like. And so what this is going to allow us to do is to more selectively extract known index streams. Here is what that index looks like. It is basically, it's called a table of contents, or a TOC. It has the contents, the offsets, and digests. Lots of information. So conceptually, the stargz format is indexed and seekable. That's what makes it different from your traditional targz. So great. We have this index seekable thing, but like, where did it come from? Like, were we just like, poof, stargz index. Huh? Well, of course, there's a tool. So there's a tool in the repository called CTR Remote. And the idea is that you can pull a container image that you want to optimize. You run image optimize. You target the container. It's going to make a new container, and then you can push it to a registry. So what's actually going on is it's running your workload in a sandbox to profile the file access. Which files are getting accessed in what order. It's going to label those files as prioritized. Like, we have to have these files ready when you start your container. And that's how it constructs that index. So basically, it's going to put these prioritized files at the top of the archive. There's going to be something called a prefetch landmark. I'll show you that. Everything else goes after the landmark and would be fetched with lazy loading. We'll talk about that. And that table of contents is placed at the end before the footer. Here is what it looks like. Let's zoom in a little bit. So here are our prioritized files. So when we have that snapshotter interface and we call prepare, these prioritized files are always going to be retrieved first, because we know that we absolutely need them when we start the container. But then we're going to hit the prefetch mark, and we're going to be like, we have everything we need to start the container. Let's commit, hand this off so we can actually have it started, and the rest of the stuff we'll get later, and we'll talk about how that works. Now, if you don't need to prefetch something so that it doesn't keep looking for it, we actually have a no prefetch landmark that appears at the beginning. So both of these are important. So great, we did this. We made our index. We pushed it to a registry. How does it get pulled, and like because what about like the other contents in the container that we might actually need later? Let's talk about it. So if you've ever looked at the OCI distribution spec, one really cool thing is that it allows you to request a range of content. Now, the use case for this is usually resumable pull. So like you're pulling, oh no, the internet cut and there's no other way. Actually, you can use the range and you can come back and you can resume. Now, this isn't like, this isn't actually a distribution spec OCI thing. This is an HTTP thing, the idea of a range request. And that's why it's so cool. You can find it in this HTTP RFC. So great. We now understand the structure of stargz. We know that it's going to have an index that describes the contents. We know that there's going to be some prefetch content, but like, what is the snapshotter doing? I'm still missing this piece of the story. Let's talk about that. So how does the snapshotter work? It's going to be serving as remote snapshotter, this proxy plugin to containerd. That means that the plugin is responsible for pairing these snapshots, the image guts that are mounted. The stargz, the E actually means the extended format, and it's extended because it provides validation, this index, and ordered content based on the file access. We are going to prefetch the prioritized files in that first call to prepare before we commit. And then for the remainder of content, and this is what took me a while to figure out, but this is where kind of like the magic happens. A custom fused file system is in fact going to lazy load it on demand. And the way that this works is so freaking cool. I cannot wait to tell you. And so throughout this process, each of these snapshots, or actually even the first one, is commit early so that you can run it as soon as possible. Okay, so now let's look at the snapshotter code. In the beginning of the snapshotter, we create a content store. The store creates a layer manager, which is going to do what it sounds like. Now, the layer manager is going to get passed around, you'll see. But we're going to start out by calling mount to the store. So in this mount function, we're going to create a new node file system. And there's some really nuanced details that are really important to note here. So note how there's a root node and a file system that takes the layer manager. So first of all, this is using GoFuse, which is a wrapper to fuse. That's really important. The new node file system is taking this root node, it's passing it this custom root node interface, and it has the layer manager. So the reason this is important, because when you look at the root node, it's actually inheriting from the GoFuse inode. And if you've used this library before, what you'll know is that when you see this pattern, that's basically saying, okay, I want to override the default function that does embed or lookup, and I want my own custom logic to do something special when that happens. So for example, the lookup function on the root node here is going to make another node called a ref node. Wait a minute, this is getting a little like Inception-y, because guess what? Whoa, it turns out to be the case that the ref node is also another GoFuse inode interface that has its own custom functions. So we have level 1, level 2. This is totally matrix level stuff going on. We're not done yet. We are not done yet. So the ref node lookup is going to create a layer node. And so at least now we have a digest to pass on. This layer node, so we're like 3 levels into the rabbit hole, and now the rabbit's like really evil, and I'm kind of scared right now, but like, let's just keep going. You're really scary. I don't want to see you. Okay. Woo. Okay, so we're in this now we're in the layer node custom inode interface. We have a few more customized functions, but for this lookup function, we're finally interacting with the layer manager, and specifically we're calling a function called getLayer. I hope that is going to do what I think it should be doing, like getting the layer, right? So getLayer calls resolve layer calls resolve. Great function naming there, by the way. The resolver is going to resolve the blob. We must be getting closer because we're talking about blobs. So just to give you the chain, we called layer resolve, which called layer resolve blob. That's going to call a remote resolve. That's going to return a blob instance. If you're familiar with the distribution spec and registries, a layer that you push or an artifact is called a generic blob. We are definitely getting closer. I hope you see where this is going. Then the blob, we're going to call read at an offset. If there's an offset, there's another name for that, a range. Do you see where we're going? So we would expect to see a very particular header, something going on in the code. Please show me this header. Okay, so read at is going to call fetch range on the blob. Fetch range is going to call fetch regions on the blob. And finally, at the bottom, we finally see the fetcher doing its worldly duty, which is to fetch. It's a fetcher because that's what it does. Okay, so finally we see this call to fetch. So when I found this function, I was like, holy cow. Maybe I said something else. Holy cow, I hope that this fetch is doing what I think it's going to do. And it absolutely did. So here we see the range header being prepared. exactly with the range that we need for that blob. I was so happy to see this. So let's just step back. What's going on here? We have mounted a custom fused file system. And so when you're interacting with that file system, like you're trying to look up a specific file that wasn't prefetched, it's calling many layers of these customized inodes functions because it wants to return an inode, right? But actually, when it does that, it's looking up exactly the content that you need, retrieving it from the registry with this particular range request. And then we expect that it's going to package it up as an inode. So is that what happens? Is that what happens? So let's go back to the layer manager where we called get layer. So actually first we're going to verify it. So remember that it had a digest alongside it. This is important. We want to make sure the blobby thing that we asked for is the blobby thing that we believe it to be. And then finally we return back an inode, which is what this interface requires. So like, that is so cool. That is how it works. That is how it lazy loads your stuff on demand. So you can probably see where this might go wrong. So imagine that you have a bunch of really big files that need to be lazy loaded. That might influence your application performance. I don't know. I haven't tested it. We would need to test that. So let's come full circle. We started calling snapshot prepare. We get back a list of mounts from that function. We then perform the mounts. We calculate the diff ID to verify that's actually a different plugin. After that step, we have a file system that represents the contents of the layer. We then commit the active snapshot to have a name. We continue applying and committing new layers. After snapshotting is complete for each layer, we use the prepared path as the container file system. And so this is the difference between sort of native or overlay. You have to wait for all those snapshots to prepare, to assemble, and then to get that final image file system. Versus with lazy loading, there's the first call to prepare with the prefetch of the stuff that you absolutely need to start your container, commit, and then everything else is lazy loaded on demand. It is so super cool. I hope you think this is cool because as I was exploring this code and what I kind of finally figured out after a very long time how it worked, I felt exactly like this bunny. I'm not as cool as the bunny, never will be. Okay, so what's the problem then? We haven't even talked about SOCI yet. What's the problem with stargz? The problem is that you have to rebuild all of your images into this very special format. And folks, I don't know about you, but I am super lazy. I don't want to do a rebuild. Just not going to happen. So this is where SOCI comes in. AWS Labs introduced it in 2022, pronounced SOCI. It means Seekable OCI. And the reason is because you're going to use your original artisanal avocado toast quality OCI compatible image, no new build needed. And the basic difference is simple. Instead of putting the index in the image that you have to rebuild, we're going to put it in a registry via the refers API. So let's remind ourselves how the refers API works. We start with a pull, we get an image manifest list. This gives us a list of platforms. We find the matching platform, we get an image manifest. At that point, the tool that's doing the request can basically switch manifest to refers to ping this other API endpoint. If the registry doesn't support that, the fallback is actually to change the colon to a dash. And so you ask for that manifest specific tag. Then, yeah, it's a little bit janky. This is the Jankmeister fake hair squirrel. He thinks he's telling us it's a real thing. We know it's not. That's fine. So however you happen to do it, you get back a refers manifest list, which might have the software bill of materials, the SOCI index, squirrel snacks. But after seeing this guy, I feel like we're definitely going to find some squirrel snacks in there. Then this is what the SOCI index looks like. Note that it is actually an image manifest. And the reason that we need this image manifest is because if you don't have the image manifest, your artifact is going to get garbage collected, and we don't want that to happen. And so then each layer in here is a ZTalk artifact. By the way, there's one of these per actual image layer. This is what it looks like, very similar. It has the file names, offsets, and other metadata that will be important to use. Here is how you actually get it, or here's actually how you generate it. Use nerdctl. nerdctl is basically going to do it when you push and you say, okay, Snapshotter is SOCI. How does that actually work? Let's take a look at that. So the way that it works is basically by calling the SOCI executable, so no redundancy of code here. And so the main difference here, I kind of jumped over this, but I'll come back to it, is that there's one ZTalk, or this table of contents per layer. And that means that in our manifest, we need to have each ZTalk point to an image layer. And we need to point the entire SOCI index to the image. And nerdctl is just using SOCI to do that. Another cool thing is that you can customize how it works. So for example, we aren't going to create indices for really, really tiny layers because like, what's the point? That we're not going to like save any time. They're so tiny. There's also different ways that you can interact and look at these things. So I recommend you try out these commands with SOCI. Alrighty, let's go back into the Snapshotter. So here again, here's the init of the Snapshotter. We see that we're retrieving the SOCI artifacts. This is where we're going to get our metadata. We then are passing the SOCI context into that same resolve function that you see on the bottom. And look, from here on, same, but different. So follow where this guy's pointing. We're calling layer resolve blob, remote resolve. That returns blob instance, blob read at, blob fetch range, blob.fetch reasons. So high level, like the only difference here is where you're putting the metadata about those regions. And so the orchestration of that is subtly different. That's the difference between SOCI and stargz. That's it. David. Okay, so I did this and I was like, I'm ready for Kubernetes. I am going to go to AWS, EKS. I am going to deploy this and I'm going to see SOCI in action. It's going to be awesome. And I went to the AWS SOCI repository and actually this was me. So these are the install instructions. I can't even keep a serious face. These are the install instructions for EKS. So I saw these and I was like, I really appreciate that someone put these together, but there's no way I want to do this, like ever, not even once. It's just too much. I was like, I want to make a Daemonset. I want to make a Daemonset because I just want one command to do the magical orchestration for me. But there was this little limitation that I saw. And this limitation makes sense. It's saying you have to configure it at node launch. The reason it makes sense, actually, it's because when you set something up, there's something called this bootstrap image. And so that's usually run by a pause container. So if you've ever looked at like the Kubelet config, you'll see this pause container. And it's doing this bootstrap process for every single container that you pull. So if you're running the cluster and all of a sudden you switch the Snapshotter, all of a sudden that bootstrap container won't be in the Snapshotter cache anymore. And it's kind of like a Spider-Man, but it's a catch-22 because you can't pull this pause container without the bootstrap, without the pause container. And yeah, that is why there's this limitation message there. Of course, if you know me, I am very stubborn. I'm very stubborn. So I was like, you know what? I'm gonna do it anyway. I'm gonna make this Daemonset. So let's first select nodes. This isn't very important. You actually don't need a selector, but for AWS, I was like, let's select M5 for X large. So this Daemonset is going to deploy a container. The container is going to install SOCI. It is going to use a trick with ns-enter to join the init process of the host, which by the way is the node, and then run the script that takes the SOCI version from GitHub. We are going to do another trick where we share files between the container and the host via a host path. Docker file, super boring. It's basically adding files and running the entry point. Here is where we're copying stuff from the container to the host. And here is where we're running ns-enter to run that script. What does that install script look like? Well, we start with a version of SOCI. Down here, we're installing dependencies. So we need the credential helper. We need Fuse. We know why we need Fuse. There's also where we install SOCI itself. Here's where we move stuff, binaries where they're expected to be. Here's where we get the service file and we reload it into systemd. We then write the configuration file. So this is where we're actually writing the SOCI configuration file. We're also updating container D to say, like, use the SOCI snapshotter instead. Here is where we're saving metadata about the pause image, that bootstrap container. And we're also logging into ECR because, hint, we're going to need to be pulling that container at some point. And then down here is where everything goes wrong because we're going to restart systemd. We're going to restart systemd specifically for container D. And then container D is going to be like, oh no, I don't have the bootstrap container anymore in my cache, like burr, burr, burr. So now we're actually going to go back to this section that I very casually skipped over. What happens down here is that the container restarts in the Daemonset. When the container restarts, it enters this install script anymore. It figures out that things are already installed, but then, and here is the incredibly stupid fix that I did that actually works. We just pull that sandbox image with nerdctl, which is already installed. And then it works. You're done. That's it. So that entire Daemonset actually works. Of course, this can be extended to support other authentication schemes or other clouds. Google Cloud doesn't need it. They have a flag, which is very nice. So summary, how is an image downloaded to a node? We start with a scheduler on the control plane. This sends a pod to the Kubernetes API. The kubelet receives it. It requests to pull an image via gRPC to container D. Container D is installed as a systemd daemon on the nodes. It has Snapshotter plugins. That's going to prepare this container root file system. The overlay default is going to require extracting them all first. It's going to take a long time. Lazy loading is loading them on demand with Fuse. And so to step back, the reason we got these crazy fast, really fast pull times is because there was like essentially nothing going on interest in these Fox containers. So like there were no files touched in the entry point because the entry point was doing nothing. So I was very skeptical. I wanted to build real applications. So I went back and I built a bunch of SPAC builds. So I built LAMPs, OSU, AMG, Mini FE. I wanted to see the output that it was present and correct. And lo and behold, it still worked really well. So you see here that streaming is the red on the bottom. Without streaming is the rusty orange. And we still are about at 1 second. It works really quickly. And guess what? All the output was there. So this really feels like magic. I mean, like you feel like we are flying. Here's a real depiction of me taking a run after figuring out how all this works and pulling containers. And it's like, oh, you're really happy. So just an aside, function naming, oh my goodness, in the Kubernetes code base, when you're looking for a function like pull image or update pod, there are a million things. I have to give a special shout out to the person that wrote the birth cry function for the kubelet. Before I saw this function, I had a very mundane view of the kubelet starting. Very boring. It's a service, like it started. Yay. This function name gave me this visual of the kubelet not starting, but screaming as it enters the world into existence. And I will never think of the kubelet the same again. So thank you to whoever wrote this function for giving me a good laugh. So something to come for SOCI that might be cool is a separate load order document. I don't know if that will help with like really big machine learning containers. So I want to quickly talk about questions that I have and work that I think should be done. So I'm interested in the kind of variation that we see in start times. Does this vary based on the application? So both of the tests that I did, it was within seconds, like a second. But under what cases, maybe some big, chunky machine learning data file that's accessed, would we actually see that start time go up to like 5 seconds, 10 seconds? I don't know. Good question. When is this not going to work well? So for example, let's say that you have really big files you have to get later that aren't in prefetch. Could that actually delay your application or do something, or actually do something worse, make it not work at all? So it's one thing to like slow something down. It's another thing to break it entirely. And my other question is like, why hasn't this become a default? So someone that's very skeptical, or they might say like, well, the clouds want you to pull the images because they're going to make more money. And it's like, the clouds are making enough money. I think there's probably like security or other issues in there that we just don't know about. So I'd like to learn about that. And just really cool, like what other, now that we know, now that we have revealed that Containerd has plugins that you can write, that you can do really cool tricks with, what other cool stuff can we implement? This is my favorite question in this list by far. So I hope that was kind of a satisfying talk. I hope that in the future, when you, well, at least for me, when you see something and either it's not clear or someone gives a talk and it's really hand wavy, read the code, whether you like to do like I do, like sit down at dinner and browse the code, or you have a different way. It is a much more satisfying meal. Hamburger, avocados, layer cake, ice cream. We have had a lot of metaphors in this talk. It is much more satisfying to really get a solid understanding of it for yourself. So on that note, if you need to reach me, I am socket1@llnl.gov. I hope you have lots of container pulling and fun adventures in Kubernetes. I sure as heck know that I will very soon.